Hello, everyone. My name is Bernt Schiele. I'm very happy to give here an invited talk at the Imbalance problem workshop at the ECCV. I think the topic of the workshop is extremely important in computer vision. Imbalance problems are really everywhere out there. And I want to share some of the work in the space related to that space of imbalance problems here from my group. Okay, so here's roughly the overview what I'm going to talk about. There are 4 blocks, essentially. One is about zero and few-shot image classification, an area they have been really working on for quite some while, actually. Then something a bit more specific about semantic segmentation, where we talk representing about a semantic projection network for zero and few labeled semantic segmentation, a space where there's much less work really than in image classification. Then I will switch gears a bit and move to a problem that is highly related to imbalance problems. And that is the bright and dark sides of scene context. And last but not least, I'll talk about a paper that is published here at ECCV this year about a semantic adversarial data generation method to enable more automatic testing and robustification of training. Okay, so the first part, as I said, will be about few-shot and zero-shot learning for image classification. And this work, actually, while there's quite a few authors here involved, it really is mostly the PhD work of Yong Jin, the first author here on the left. And actually, the slides I'm going to use are essentially his that I have been stealing from him the other day. Right. So let me just give some motivation, even though obviously it's not really necessary here in the context of this workshop. But deep learning had great successes in all kinds of domains, like self-driving cars, AlphaGo, you name it. And one of the things, obviously, that one can argue is that the 3 most important components are the network architectures that we're having. We're improving them over the time. We have lots of data, typically supervised data that we can use. And then we have the processing power from the GPUs. But the key is, and that's actually the central theme in my view about the imbalance data problems in computer vision, we do not always have sufficient data to train our networks. So the way I like to look at this problem is that we essentially, pretty much all the problems we're having, we're looking at a long tail distribution. For some of the data, like say in image classification for cars or even some cats, we might have a sufficient number of training images to really train our classifiers. But then for others, like for special species, for birds or other classes, right, they're just not as frequent around. We don't even have the data and not even the labels, both of that actually not really. So then we have a problem that we need to train our networks with much, much less data. And they're really sort of the terminology I'm going to use for the first part of the talk is that for the base classes, we're assuming we're having a reasonable amount of data, right? That's 20, 100, or even 1,000 of training samples per class. Then we have something like noble class, where we have either very few samples, like 1, 5 or so, right? And then zero-shot, we have no training data whatsoever, right? So that's sort of the extreme case of this long tail distribution problem. And then sort of the classic baselines, what they're doing is they're defining some base classes where you have a reasonable amount of data. And for the noble classes in the few-shot setting, you have sort of a little training data, like 1, 5 or so samples per class. And then during testing, you're testing essentially only on the noble class. That's the classic and standard setting. I'll argue in this talk, this is actually not particularly realistic, right? So if you only have the result or the performance on the noble classes, this doesn't tell you much really how the system will do if you also have base classes available during testing, which is really the realistic case. You want to still recognize the cars and the cats, right, when you have other bird classes. So it's really, you really should look at this generalized setting where you have both base and noble classes during testing. So that's for the few-shot learning case. For the zero-shot learning case, it's essentially very similar, right? Except that now we're also having some semantic embedding because we don't have any images for the noble classes. The semantic embedding most classically would be some attributes, like in this animal with attribute data set, the ABA data set, or often also some semantic embedding like word2vec is used here. So we have this semantic embedding, and that is then used to guide sort of essentially the algorithm to also perform reasonably well on zero-shot classes. So the test set, again, the classic one is that we don't have any base class images during testing. We only see sort of the noble class performance. And again, I'll argue that we really should look far more frequently and more thoroughly actually at the generalized zero-shot learning case, where we also have test images from the base classes. So I don't want to give an overview here of all the methods that are out there for zero-shot learning or for few-shot learning. There are too many to name here. But I want to as I said, highlight some of the work that I've been doing in that space and compare also then to the state of the art. But before we get there, let me briefly mention one piece of work that we've been doing sort of at the beginning when we looked at this problem. And we sort of found that there's a number of issues with the previous work, at least at the time, in zero-shot learning. The first one is it's relatively hard to compare results if you look at the papers, because there was no real standardized test set. There were sort of a number of data sets, a number of splits that people use, and also different evaluation metrics. So in the CVPR 17 paper and then the follow-up paper, the PAMI paper, we tried to unify this, right, and basically sort of gave a pretty clear evaluation protocol, the splits and everything else, the evaluation matrix and metric and whatnot, to make this more homogeneous. And lots of people have been starting using this, just to mention this. One key thing actually, which was quite interesting to see, is that because people do feature pre-training quite often on ImageNet, right, before they do their favorite zero-shot learning approach, if the novel classes actually overlap with ImageNet, this is not a zero-shot learning task anymore, right? So we had this flawed splits actually that people have been using for quite some time, and we basically cleaned them up, right? And so I really encourage you to use these new class splits if you're interested in this area. And last but not least, and I already mentioned that, right? Most people basically did not look at the case where base classes are, present during testing, right? This case is the classic setting here, that only the novel classes are tested and not the base classes. And as I said, the generalized zero-shot learning is a more realistic, more interesting case in our opinion, and such we really have sort of, also defined this here in the in this benchmark. Just for mentioning that there is this benchmark out there that you can actually use if you want to compare to other people's work. Just to make the point that this generalized zero-shot learning really is key or important to look at, let me just sort of here for some approaches here, for some of the approaches we benchmark in this benchmark paper, right? There's a huge gap really between the base and novel classes. So here the red bars are basically much higher. These are the performances of the approaches on the base classes, much higher than for the novel class accuracies, which are the blue bars here, right? And if you use the harmonic mean as what we propose to measure basically the balance between the two performances, right, you can sort of judge sort of what has a reasonable trade-off here. But really, we should look at both the novel classes as well as the base class performance. Okay, that's good enough, right? Just I wanted to mention this benchmark in case you haven't heard about this. Okay, so now let me talk about how we think, or one of the approaches that we think are particularly intriguing to use in the case of zero-shot and actually also few-shot learning. That's essentially about a generator, right? It's trained in an adversarial setting where you basically have some semantic embedding. Again, think about your attribute vector or some word-to-vec embedding for your class. You have to build a bit of noise and you start generating images. You can train this on your base classes, right? And then you get a generator, and then you're getting images for that for those classes. And you can do this also for the novel classes. So what's the catch here? What's the problem? The problem really is that the images that you're getting here are not particularly realistic. It's in a sense a too hard problem. We have seen sort of extremely convincing results when generating phase images, but phase images is a much easier problem. It's a pretty constrained problem, so that's where most sort of generators are particularly good at. But if you want to generate sort of a large variety of animals, let's say, or other kinds of object classes, right, you're having a much more trouble. So what you looked at actually instead of generating the images, we basically argued that we should rather generate feature vectors. You can really think of a ResNet feature vector that we're generating here. So for the base classes, we can use our pre-trained ResNet network and generate the real features. So now our generator's task is, instead of basically generating images, it really is supposed to just generate sort of features, ResNet features, for example. Right? And then you have the adversarial setting where the discriminator basically sort of ideally cannot distinguish between the real features and the generated features from your generator. And just to make the point here, this generator actually is pretty simple, right? It's just an MLP, a few layers MLP, right? It's a multi-layer perceptron, pretty simple generator you need here for this. And again, right, so you're training this essentially on your base classes. That's the blue color that I'm using here for the base classes. And then you can use your novel class embedding and still generate feature vectors for those novel classes. we have actually one additional component here that we added here in this UPR 18 paper, where we had also used the classifier as an additional source of information for updating our generator. And the classifier essentially on your novel class, on your known classes, the base classes, you know actually which class labels they are, right? So you basically can train a classifier, and if the classifier is not good at differentiating your features, right, which you know you should be able to differentiate, you can use this as an additional signal. So I have this classifier signal as well as the classic discriminator signal in this GAN training. So just to make the point quickly that really this is quite different than quite a large number of the zero-shot learning literature. A lot of the literature in zero-shot learning, what it does, right, it has the semantic embedding space. What you're learning is sort of taking your images and you're trying to map this into the semantic embedding space, right? Sort of the image is directly in here, for example. And then because you have the embedding for the novel classes, if you have a new image of an unknown class, you map it in here and you hope it falls in a similar spot than the semantic embedding of your novel class, right? So that's essentially then just a distance function in this semantic embedding space. This is quite different, right, from normal training. Normal training, we have just sort of some feature vectors and train a classifier on top, essentially. And now that I have my generator, which actually just generates features both for the novel and for the base classes, if I want, I can just use those features. Typically, for the base class, we use the real features, and for the generated, use the generated features for the novel classes. We can train our classic favorite classifier classically just with cross entropy. That's quite different, and it turns out actually this actually is more. It's easier, it's not only easier, but also gives us actually better performance. Just to drive the point home that the generator, that is pretty simple, as I said, it's just a multi-layer perceptron, actually does quite well. Let's have a look how well I can generate features for my base classes. So here, basically, we're checking how good this generator can generate features for my base classes. So if I use the real images, I get this performance, which is some 70-something% of classification accuracy. And here, the orange line basically is the performance I'm getting if I start training my generator, right here in that particular case on the cup data. And eventually, basically after 200, 300 epochs, I'm having using just generated features with my generator, I'm getting only a few percent points loss here in the overall performance. So that's quite interesting that really the generator can generate quite powerful features that are good enough then for classification later of the real images, obviously, again. Okay, so here, so here are some of the ablation studies we did, right? So if we have a standard GAN here, right, which is classic, Goodfellow loss, that's a standard one. If we use then here the Wasserstein loss, right, the standard Wasserstein GAN, basically slightly improve. And the one classifier that I said mentioned earlier, right? Sort of if I add this classifier into my training, right, on the during the generator, I can further improve. So I really can push here basically with each of these components that we talked about the performance here. Right. So here then is some data here on sort of the generalized zero-shot learning. So this is the generalized zero-shot learning abbreviation that I'm going to use. So if I use the real images and some, top performing sort of method like ALE, right, on the novel classes, it is doing reasonable, but actually this generated feature work actually does quite a bit better. We lose a bit of performance on the base classes, but overall, again, in the harmonic mean, we're having some 15% point improvement. Okay, so that's sort of some idea. Really generating the features rather than generating the images gives us actually quite some performance boost. Actually, we also in that paper we also compared it briefly with sort of generated images, and it's clearly that generated images cannot give us anywhere close to the same performance. Okay, so we all know that these GANs, the generative adversarial networks, have a particular problem, which is actually mode collapse, right? So it's very hard to generate multimodal distributions of features, and that's the same problem in a sense we're having here. So here again, it's the same. It's just a little bit of a drawing. The drawing is a bit different, but it's really the same architecture that I had before, right? We are having here a generator. It's just a multi-layer perceptron here, as I said, to generate my features, and again here then my discriminator that looks actually here a conditional discriminator that has the embedding here and the features, and should not be able to discriminate between the features from the real images and from the generated features. Okay, so one thing that has been argued is that we could actually use a variational autoencoder in combination with a GAN, and that's exactly what this upper stream here is, right? What we're learning is here we have feature embedding still the same as before. That gives us the feature. Now this feature is actually encoded to get sort of here this latent code that is ideally the same as here on that side. We're using here the classic code-by-like-bit versions as a constraint that it's this Gaussian distributed. And then this one here basically is using the Zane generator as the GAN model, right, to generate back my feature. So I have an encoding, decoding, where the decoding here essentially is now the, the generator. Right, and then I can use this here again to train my, I can have additional information or different branches here to improve my generator. That's what we'll see actually is, or what we have seen in this paper. In that case, it was a CPR19 paper. We actually do improve here for the novel classes by several percent points on the base classes as well. We also improve, and overall then obviously also in the harmonic mean. So that's the zero-shot case that we can also obviously use now in the few-shot case. And here again, I'm comparing this to two sort of state-of-the-art methods here, imprint and analogy. And as you can see, our method here that has this VIE-GAN, this combination of a variational autoencoder and the GAN method that I talked about actually is really improving performance quite a bit, in particular in the low data ratio. If I have only 1 or 2 data samples per class for the novel classes, I'm really improving a lot here the performance. Okay, so we did one more thing on top, basically, also in the CPR19 paper, where we basically also applied this to the transductive zero-shot learning. What's sort of the key thing? The key thing in the transductive setting down here, we have the classic setting, right? Base classes, semantic embedding, and training testing have the base and novel classes. Transductive setting, by definition, is essentially that we have the novel class images also present at training time. However, we don't know the labels, obviously, so that would be too easy, clearly. But in this transductive setting that's been argued a long time ago, it's a very interesting setting that you also have the images, but not the labels available. So how do we use them? Well, we are adding, so here another branch down here, right, where now we're having sort of, we also, for the novel class, we can take the images. We don't have the labels, but we can take the images and calculate the respective features. Now we have an unconditional discriminator that actually looks at those features and the features I'm getting here out of my generator. And again, this one, this discriminator should not be able to discriminate those two, right? And again, there's an additional signal here for the generator to improve its generation of image features. Right. Yes, and then we have all 3 losses here essentially together, right? The 2 adversarial losses and the VIE loss here as well. Okay, so what does it do? So actually, it does quite a bit of further improvement, right? So here are the 2 performances that I talked about earlier, right? Sort of this for novel classes, because now I'm really having access to images of the novel classes, not on the labels obviously, but on the images. This improves the generator's performance quite a bit. And such, therefore I can basically here also improve, and I also improve on the base class actually, as well as the harmonic mean again together. And again, we can do a look at this in a few-shot setting. And again, I'm comparing it to 2 state-of-the-art methods. Here, right there, the state-of-the-art methods. So that was the previous approach without this transductive setting. The transductive setting actually is then improving further. There are actually other methods that are also using the transductive setting now. Most of them improved a bit, right? But still, this performance, these numbers are pretty competitive also today. Okay, so then let me switch gears a bit and come to my second topic, which is about semantic segmentation. And again, this is, you know, the lead author is Young Chin. This was actually joint first author work with Supa, actually here, the second author on this paper. Semantic segmentation, we know it's very tedious to get sort of sufficient amount of training data. So it actually is natural to think that we want to reduce the amount of training data to either 0 or even few-shot learning, right? So in the zero-shot case, again, we're thinking about having some semantic embedding, right, of my respective classes, but I don't have any single training sample here. And I can do the 0-labeled semantic segmentation. And if I have a few labels here, like for example, for the giraffe class, I can also use the semantic embedding as well as sort of the few labels here to improve my semantic segmentation. But how exactly to do this? And what we came up with here actually is a pretty simple, surprisingly simple approach that actually also works surprisingly well. So let's look at the standard pipeline, right? The standard pipeline is that we have an input image. We have some segmentation network, your favorite segmentation network that you have here. At the very end, you have sort of a some one-to-one convolution that you get pixel-wise predictions over all the classes, right? All the classes you're interested in. And if you have the ground truth, right, you use the classic cross entropy loss, for example, right, and to basically backpropagate here to improve the network's performance. Okay, that's the classic thing that we obviously can't use because we don't have ground truth for classes that we like if you have zero-shot semantic segmentation, we have not a single limit, so we have no ground truth data whatsoever, so we can't really get any signal for those classes. So we slightly modify this architecture here in the middle in the following way. So we take the input, right, still have a segmentation network, and basically here we're having here an embedding feature space, right, that actually has sort of a certain dimension for the height and width, and some embedding some semantics here, dimension here, just some feature tensor, right, as we all have sort of in the CNN feature hub somewhere in the architecture. And then I'm basically multiplying this, just the matrix multiplication with my semantic embedding. Remember, I have a vector for all of my my data for base classes, for my novel classes. Here, I'm only using the base class embedding. I'm using that, and that matrix multiplication gives me, again, a pixel-wise prediction, right? This pixel-wise prediction now I can train just normally. So it's just this matrix multiplication now makes it more semantic what's in here in this feature channels here. And as I said, right, it's just standard cross-entropy loss that we can use here. So how does it help? Well, if you have the novel classes now, you only need to replace the semantic embedding with the novel class embedding, right? You're just taking here the novel class embedding right there. And then you get, without any retraining, you still get pixel-wise predictions for those novel classes, right? So you're getting here, for example, cow pixels classified, even though in that particular case, we didn't have a single cow image or cow class pixel annotated for that data. Right, so here there's actually, there's some few shot papers that look at semantic segmentation, but they're not exactly comparable to us. So here we're really looking at the performance more on absolute level, how far we can get here. So with cross entropy loss, actually we get to some 33% using fast text as a semantic embedding. We get to 32 mean IOU, sorry, I didn't say that, mean IOU here. With the work-to-vec, and if we combine both of them, right, in this matrix multiplication, we get even slightly higher. But actually, that's pretty impressive, right? Getting 35 mean IOU, right, with having not a single image for annotated, right, with that particular class, that actually is pretty high. An interesting catch here is if I replace basically the cross-entropy loss with hinge loss, which is a very classic loss used in zero-shot learning, actually, this drops actually quite a bit. That's just sort of a side note here. If I use hinge loss, really isn't as powerful than the cross-entropy loss for this problem setting. So let me give you a bit of qualitative results here to give you some impression. So here is an image, right, with cows, obviously, right? That's the ground truth that I'm supposed to get. And if I don't have a single cow pixel annotated, so zero labels, I'm getting here the cows pretty nicely already, right? So here for other object that works also quite well. For the giraffe, it doesn't quite work, right? Zero label, giraffe is apparently too far away in its appearance, and then even the semantic embedding doesn't really capture this kind of changes. So if I have a single label here, a single image now labeled with the class, here I'm improving, right? Also here slightly improved. Now the giraffe actually starts to appear. If I have 5 labels, right, the cows are getting even better, right? So here I still had problems in the background, and the giraffe becomes also better. But still, like with very few labeled samples, I can go pretty far in this performance here. Okay. So now, as I said, sort of for the third part of the talk, I want to really switch gears quite a bit. Not talking about the classic zero and few shot settings, but talking about the different problems, which are also very much related to imbalance problems in computer vision. The first one is actually about scene context. This is really about 2 main papers. This first part I want to talk about. The one is adversarial scene editing at NeurIPS 2018, and the second one is about not using the card to see the sidewalk. Let me just briefly say or show you what the problem is. Okay, so here, if you look at an image like this one here, that's the original image, right? Sort of an well-performing semantic segmentation network, right? Like UPONet, right? Gives you really sort of the sidewalk here, the road here, building here. Does a very good job on that particular image, right? It's nice. Gives you high numbers, right? All good. So now if you take the same image here, and what we did here in that particular image, we edited, and I'll talk very briefly about how we did that. So we edited out here the cars on the left side of the street. So now it's quite interesting that actually these cars that are missing now on the left side of the street actually corresponds or cause a a change of performance quite drastically on that right side of the street, right? Which actually the sidewalk is not really found anymore. All of a sudden, it's kind of the road that is hypothesized. On the very high level of the abstraction, you could argue, well, okay, actually, when there's cars parking on the left side of the road, that actually is a reasonable assumption. Actually, when they're parking, that there could be a higher likelihood for sidewalk on the right side of the street. But actually, if you think about it, it's actually, it's a context that is actually overused, right? It's great if the context helps, but here it destroys literally if the context is missing. It destroys the performance here, right? So what we wanted to do in this work is actually, twofold things. Actually, we wanted to, on the one hand, quantify this context sensitivity, right? And that really is what this NeurIPS paper is essentially about. But then also use, in our case, what we're doing is we are removing objects from the images. We're removing the objects, and when there is a problem, right, by removing this object in the performance, we basically use this as a data augmentation scheme to improve the performance of the final classifier. And here's sort of another example I'm going to show here also again later. So here we took out the cars here on the right side of the road, right? And if we take that out again, right, so here now it hypothesized all of a sudden there's a sidewalk, while actually here correctly in the original image, it was actually classified as road. Right, so I'm not going to talk a lot about the NeurIPS paper here, really. So where we basically had sort of an entire paper about how you really, carefully can remove or train a network to carefully remove sort of the an object. But here's your examples here, right? From that image, we are removing sort of the dog, right? And you have an image now that really the dog is gone, and there's little artifacts actually in the image. So here the upline is actually removed, and yes, you see a bit of artifacts, but still, right? So this is still using or usable for doing analysis, and also if you use that for training, you can always test on other out of distribution data. That's exactly sort of the idea, right? We take the original test image, right? We automatically remove individual objects, just saying, okay, I want to remove the dog. I don't have any bounding blocks, just say where I want to have the dog removed here. And then I have this image here. In that particular case, it's actually an image where, so here is the keyboard is removed, here's the monitor is removed, and here is the mouse removed, right? So I have three different versions of the original image, right? I have in each where one object is removed. Then I look at my target model, if it still does what I'm wanted to do, right? For example, detect that there is a screen here, that there's a keyboard, but there's no mouse here. So basically check what it actually does. And when it doesn't do the right thing, I can use it then basically the data to this particular image actually to augment my training data and actually use that additional training data to improve the overall performance. And that's exactly what we're doing in every epoch, right? We're removing objects from images, check if the network is still doing the right thing. And if it's not doing it, we're adding it to the data for training. That's the brevity I'll give it here. There are obviously more details in the papers, and if you have questions, then during the question and answer session, we can also talk about this later. What I want to show here is a bit of these results, right? So this example I showed you before. We take the original image, we remove the cars. So the UPANET is state of the art, right? So it does well on here, but actually does not well here. If we now retrain UPANET with these data augmented versions, right, basically we do a better performance here for this case. Here's this case I showed you also earlier, right? Here on the left side, we have the cars that were removed here in that image. Here, the UPANET actually has problems here with the sidewalk, and if we have data augmented it, we are getting here the sidewalk data. Let me show you two more examples. One I find particularly striking because it actually has a huge area of the image actually is completely wrong, which is this one here. So here we have the original image, right? And here we basically remove the trees here in the background, right, of the image. And now because the trees are missing, right, UPANET, what it does basically tells down here is earth, right? It doesn't say it's any more grass, as it said before. So somehow the trees are used to actually infer that the grass is there. So it's kind of a context information that, well, kind of intuitive, but it's overusing the context, I would argue. And then if we retrain, we do better. And then maybe this example, which is most related to the imbalance argument of this workshop. Here we have sort of the original data with the car here. And then we basically, if we edit this car out of this or have it automatically removed from that image, right, sort of UPANET actually goes a bit crazy, right? It says still road here, but it says water and earth here. And intuitively, this is sort of an example really far in the tail of your distribution, right? So you have not many examples of cars driving in winter to start with, then in particular sort of, how the street looks and how the snow on the left and right side of your street looks. It's going to be very, very hard to have a reasonable large scale amount of data for these kind of cases, you really are in this imbalance space, right, where you can't ever have enough data anyway, right? So you could obviously go out and try to collect this, but somehow this is, it's doomed to fail, right? Because there are going to be also other cases, corner cases in the imbalance problem that you have to deal with. And if you're starting sort of more explicitly searching for them, which we are sort of doing by manipulation here with the images, we can actually at least partially overcome this problem. Okay, so that brings me to the last paper I wanted to briefly talk about here today, which is, as I said, an IPCV 2020 paper, which is about towards automated testing and robustification by semantic adversarial data generation. Okay, so here, what's the problem? So we're looking classically, right? In our computer vision, we have training data and the test data that are, sampled from the same distribution. We call it IID, right? Independently, identically distributed. And often this is sort of perfectly fine. If the training test data is drawn from this, we're typically quite happy with the results. And then we look at the results and look at the performances and declare it has that performance. However, if you're starting going out of that distribution that we had during training and test, actually, right, from both of them, by, for example, adding noise or actually adding or changing the context information, we're often getting, very bad test results. That again is sort of a bit of an imbalance problem issue in my view, because during training and test, I have a certain amount of data, right? And in the test set and the training set, certain data actually is present only to a small degree, but still it doesn't really show up in statistics. So if I basically oversample these tails or even generate images that were neither in training or test, right, which are really semantically totally plausible, I'm really gonna see that actually my performance of the model is not as good. So somehow evaluating on a predefined training test set, right, that is IID even from your domain, right, at the end of the day, might really overestimate eventually the performance you're going to have really in real life, where you're always going to have some distribution shift, right? Okay, so here that's sort of the picture we're having is something like this. So it's a pretty full slide in order getting the picture, but I'll try to walk you through. So your model, right, has this in the screen area, has the correct predictions. On the training data, it is trained, it does all well on the training data. On the test data, it does pretty well, except some small part, right? But you're saying, okay, that's my error, and I'm happy to accept this. But then, you're estimating a certain performance on the test data. So, but there's still, if you were able to search for them, right, and that's exactly what we're aiming for, that really error cases that really sort of far beyond, right, your decision boundary, but still might look actually like true positive example that you should actually do correct differently. So that the true boundary for the classification is maybe here. If you were able to find those cases, right, by searching, by essentially gradient descent, that's exactly what we're doing, by gradient descent to find actually error cases that are neither in your training nor in the test data, but still, semantically plausible, then you actually could identify error cases. And if your error cases, you're thinking these are really error cases you want to handle, you can go back obviously again and use this for data augmentation. So here's an example, right? We have the cow here. That's a part of the data. In my training data, we're starting to manipulating the cow by adversarial training, but not small adversarial patterns, but really sort of, cross kind of changes in the appearance. And here we're getting an animal that most humans actually would still call a cow rather than a horse, right? So you can obviously argue that if these examples are realistic or not. They did the user studies from the kind of images we're generating. 93% of the cases, people agreed that actually it is the same label still, right? So in that sense, the data we're generating eventually actually has, from a user study perspective, high confidence. And the way we're doing is we're having a generative model, right, as well as an adversarial attack on my classifier combined. So in a nutshell, and that's sort of, I know it's a very high level view on this approach, and there is a 2-minute and a 10-minute presentation also on the IPCV conference webpage, right, because there's an oral paper during the conference, and it really has 3 main components, right? So from an input image, we want to synthesize examples of the same class still, right? For in that case, the bird. And the synthesizer actually, sorry, the synthesizer separates the shape and appearance here of that object. The appearance we're actually getting here from an appearance convex hull. We have a latent space where we index sort of the appearance. That's sort of part of the training that we learned this latent space. And we're staying within the convex hull of here, the bird class, to generate sort of a new appearance for the bird, right? You're always selecting actually 5. You don't take the full space of all appearance. You only take 5 or a small number of appearances for the bird class, and then we stay within the convex hull. So the synthesizer generates a new, using the pose and the shape here from the original image, generates a new appearance. And then once we have this new image, we'll take our detector. We get sort of a loss for how well it actually does, and then we basically backpropagate here through adversarially, so essentially, right, to update the synthesizers that actually getting a new image. So you have the synthesizer, right, which has this disentangled shape and appearance representation. The adversarial optimization, right, which is here semantic because we have to stay within the appearance constraint of the convex hull of the class, or subset of examples of that class. So you could argue, obviously, this convex hull there's no guarantee that actually this really sort of gives us images of the same class. That's absolutely correct. In practice, though, we see that actually this is pretty good. As I said, 93% of the cases we're generating are still resembling, our original class. Okay, so here just some examples here. Here you're starting from this original image, right? In the first iteration of optimization, we're changing here the appearance, right? Here is further changed. So when you see the BERT so score goes down slowly at least. And at some point here in that particular case, in iteration 6 of the optimization, it all of a sudden actually really classifies as dog with very high confidence, actually, right? 0.8 score here. And then there's a dog as well as a frisbee. So even though this one now really looks like very much like a bird, right? So it's still a bird, a chicken bird, obviously, but still is a bird. And we have seen here sort of on Coco data, right? If you use the original, I think it's a YOLO detector, we get 81% or so mean precision at 0.5 overlap. And if you manipulate one object in an image, right, you can drop this by 22 percentage points. And if you have if you have two objects manipulated, you can even further drop this. And as I said, right, sort of in those cases, we showed this to humans, right? They were saying, no, that's the correct class that still was there originally. They also gave that as a label for those classes. So how do our semantic adversarial examples look like? So here, a case that we have quite frequently is something we call camouflaging, right? Basically, the object actually becomes sort of very much, merged with the background in terms of colors, right? So that's the original stop sign. That's sort of the one that actually comes out. And here, there's no detection anymore. Even humans would immediately say, yes, there's a stop sign. You might argue it's not a very realistic one, but actually still it's a stop sign. Here's a case where it generates hard examples. So here there's a motorcycle, right? And then our semantic adversarial generator generates here a motorcycle still, I would argue, right? Very much so, but it actually is classified as backpack. So it's really completely off. So really generating hard examples in terms of appearance. And here, that's maybe the least surprising one, I suppose, is if you're having sort of a particular object like in a context that is unusual, like a person in the sky, in the case of skier. If you do the semantic adversarial generation here, you can quite easily, by changing a bit the appearance, generate something that actually would better fit the context here, in that case, an airplane, right? And obviously, there's more examples in the paper in the supplement. So, okay, so how we're doing and how is this working for then also if you do data augmentation? And if you actually use IID test data, you're not improving that much, and that's not too surprising because you're generating data that actually really is out of the test data distribution as well. The test data is also IID from the original training data, so you're really not generating. You're really generating things that are not, represented well in the IID test data. So in that sense, it's not too surprising you don't get too much improvement on IID data. On the out of distribution test splits that also exist for these data sets, right? So you're basically improving quite a bit more, which is what proves a bit the point that that if you're searching for really sort of difficult cases with this method that I was talking about, you really can get better on this out of distribution or far away kind of cases that are really sort of important really to solve better in this kind of context. Okay, and that brings me essentially to the end here. Just one last slide to this last part of the talk. There is a web page where you can also find the code, right? It's what we call semantic adversarial manipulation. And as I said, there's an oral presentation during the conference where you can find a 10 and also a 2-minute video giving some more details. Well, that very much brings me to the end. Again, thank you very much for giving me the opportunity to talk a bit about some of our work in the context of imbalance problems in computer vision. And I'm very happy to take questions. In a week's time, we can have the question answering session. Okay, thank you very much and have a nice day.